Now let's look at a concrete example of how to formulate a linear programming problem. And we'll use a very common application in linear programming that is called product mix problem, where you have two or more products that need to be produced using limited resources. So which product mix will give you maximum profit? So that's the essence of what a product mix problem is. So let's look at an example. So we have a company that produces and sells two different models of computers, Basic 1 and XP. Okay, so two products. And the profit for Basic is $80 per unit and XP is $129. Okay, so our broad understanding here is that how many units of the two models we should produce so that we can maximize profit. And here are some restrictions. So we have sales is estimated to be 600 and 1200. So we don't want to produce more than the estimated sales, because if we did, then we won't be able to sell all the production. So we want to keep the production within 600 and 1200 for these two products. And then there are some resources that are needed to make the computers, and there are two operations. You have assembly. Assembly requires 5 hours of labor for each basic and 6 hours for XP model. Then you have a second operation, that's testing. Testing basic requires 1 hour and XP requires 2 hours. Now these two resources are available in limited quantity. So you have 10,000 hours allocated for assembly, 3,000 hours are available for testing. So this is the broad understanding of what the problem is. So the next step is to define the decision variables, and that's the most important step here. The decision variable here is we want to decide how many units of each of these two products we should make so that we can maximize the profit. So the company wants to know how many of each model to produce. All right. So the problem objective is use LP to find the best mix of the computer models to maximize profit. Stay within the labor availability. Don't produce more than what can be sold. So this is your broad understanding of the problem. The decision variables or number of basic computer model, okay, let's call it X sub 1, and number of XP computer model, let's call that X sub 2. So now profit for basic is $80 a unit. Okay, that's given. And XP is $129 per unit. So with X sub 1 representing number of basic models and X sub 2 representing number of XP models, the total profit will be X1 is the number of basic and $80 is the profit per unit of basic. So 80 times X sub 1 will give you the profit that we'll make from the basic model. And similarly from XP model, we will make $129 a unit, and we're going to be producing and selling X sub 2 units of XP model. So 129 times X sub 2, and add the two, we get the profit. So 80 times X sub 1 and 129 times X sub 2. So that's the total profit. And that's what we want to maximize. We don't want to minimize profit, we want to maximize profit. Now we have constraints, right? So we have labor hour constraint. Okay. Assembly labor, we need 5 hours for basic, 6 hours of XP. We have 10,000 hours available. Testing, we need 1 hour for basic, 2 hours for XP, 3,000 available. And then we have sales constraint, 1,000 and 1,200. So these are the constraints now we have to express in terms of X sub 1 and X sub 2, the decision variables that we have defined. Okay, like we used the decision variables to come up with a mathematical formula for the profit, we have to come up with mathematical functions for these constraints using X sub 1 and X sub 2. Okay, let's do the labor constraints first. And still remember, X sub 1 is basic, X sub 2 is XP. So here let's look at the assembly labor first. So X sub 1 is the number of basic. 5 hours of assembly is needed for each basic. So 5 times x sub 1 will tell us how many assembly labor hours we need for basic. And similarly, 6 times x sub 2, 6 hours per unit, and x sub 2 units of XP model. So 5x sub 1 plus 6x sub 2 will give us the total assembly hours we will need. And we have to stay within 10,000. So 5x sub 1 plus 6x sub 2 less than or equal to 10,000. And similarly, testing, okay, we need 1 hour for each of basic. So x sub 1 times x sub 1, so just x sub 1, and then 2 times x sub 2. That will give you the total testing labor that we will need. Okay. And that has to stay within 3,000. So these are the two constraints for labor hours. So we still have the sales constraint. Okay. So we can only sell 1,000 basic and we can only sell 1,200 XP. So with x sub 1 and x sub 2 representing these two models, x sub 1 has to be less than or equal to 1,000 and x sub 2 has to be less than or equal to 1,200. So that these two will then take care of the sales constraint. So putting all of this together, then our linear programming model is maximize 80 x sub 1 plus 120 x sub 2. Oftentimes we can write this as z equal to. A lot of people write the objective function as z equal to the function. And subject to these two assembly and testing hour constraint, labor hour constraint, and then sales constraint. Okay? And of course, the non-negativity constraint, this is called non-negativity constraint. Non-negativity constraint should be added at the bottom of all algebraic models when you are formulating linear programming models. So non-negativity is a requirement, so you have to identify that at the bottom. So this is how you would go through the process of formulating a linear programming model.